In this lecture, we'll discuss the Carnot cycle and its efficiency. So, in the previous lecture, we've seen that the thermal efficiency of a heat engine cannot be 100%. Then, can we ask the question that is there any limit on how efficient heat engines can be? This question was addressed by Carnot, and the cycle introduced by him is termed as the Carnot cycle, on which the engine described by Carnot operates. So let's consider a heat engine that operates on a Carnot cycle, and the working substance of this heat engine is a fluid that is homogeneous and a pure substance. Therefore, the state of the substance can be described by two variables, and let's choose these two variables as the mechanical variables, which are pressure and volume, and we'll use these two mechanical variables, pressure and volume, to define the state of the system. And recall from the zeroth law, we know that these two mechanical variables, pressure and volume, are related to a thermal variable, which we'll denote by theta, and this theta is what we call as temperature. Note that we'll use the symbol theta to denote temperature, which can be measured by an aid of arbitrary calibrated thermometers such as mercury in a bulb thermometer or a thermocouple. And we'll not use our symbol T to denote this temperature, because we'll reserve this symbol for the absolute thermodynamic temperature that we are going to introduce using the Carnot cycle itself. So theta is the temperature that is introduced by the zeroth law, and this temperature can be measured such as using the length of the mercury column in a bulb thermometer, or using the EMF in a thermocouple junction. Because we have a homogeneous system of a pure substance, we need only two variables. So let's say this is pressure and volume, and we can say this is specific volume. So the Carnot cycle consists of two isotherms. So this is the first isotherm, and this is the second isotherm. So let's say you are initially at state 1, then first you expand this fluid while going from state 1 to state 2 while keeping temperature constant, and let's say this temperature is kept constant at theta equals to theta 1. Then you go from state 2 to state 3 in a reversible adiabatic process. And note that because we are plotting all these processes as paths using solid lines, we mean that we are having reversible processes only. Now you reach state 3, and from state 3 you again undergo an isothermal compression where the temperature is kept constant at theta 2, and theta 2 is less than theta 1, and you reach state 4, and from 4 you go back to 1 again in an reversible adiabatic process. So in this Carnot cycle, heat is added to the system from a high temperature reservoir at theta 1. So you have a high temperature reservoir at temperature theta 1 and a low temperature reservoir at temperature theta 2, and heat is taken from this high temperature reservoir theta 1 during this process, and which we'll call as Q1, and we have a cyclic process, and heat is rejected during this process going from 3 to 4, and we'll call that heat as Q2, and in the whole process, this heat engine that operates in a cycle delivers work which is equal to Q1 minus Q2. Now, why do we have this particular cycle and not any other cycle? So what we want is a heat engine which is operating in a cycle, but in particular we want to have a reversible heat engine that is operating in a way that it takes heat at high temperature theta 1 and discards heat at low temperature theta 2. And we'll see that the only way you can have is through this Carnot cycle, so that you can operate this heat engine reversibly in a cycle. Now, to see how this process can be realized, one way is to consider that you have your familiar piston cylinder arrangement. So we have this frictionless piston fitted on this cylinder which contains gas, and note that the working substance can be anything. It need not be an ideal gas, it could be anything which is a homogeneous system of a pure substance. Now let's say that you want to go from state 2 to state 3 through a sequence of equilibrium states, and such a process we've seen earlier is called a reversible process. So if you want to go from state 2 to state 3, that is an adiabatic process, then how can you go about is that we've seen this earlier, that imagine that there is a pile of sand on this piston. Then if you remove one sand particle at a time, then you can slowly expand this gas in a quasi-static manner, and the piston rises up and there's no heat transfer to the gas, and as a result the volume will increase and the pressure is going to decrease. So you can go from state 2 to state 3 in a reversible fashion, and because you are lifting this weight of this sand over this process going from 2 to 3, you are doing net work. So the system is delivering net work. So this is how we have seen earlier we can reversibly expand or compress a gas in an adiabatic process. Now similarly, heat can be added or rejected in a reversible process during an isothermal process. So let's say again, in the same system, that is this piston cylinder arrangement, we want to have heat transfer in a reversible manner. Then we know that the temperature difference is driving this heat transfer. So by reversible heat transfer, we mean that the temperature of the thermal reservoir from which heat is being extracted, let's say is theta, then if you have infinitesimally small temperature difference between the system and the thermal reservoir from which heat is being extracted, then heat is said to be transferred reversibly, because you can change this temperature of the system infinitesimally and you can reverse the direction of the heat transfer. Now, if you want to extract heat, that is, our heat engine wants to extract heat from a high temperature reservoir or to reject a low temperature reservoir, and if we have to do it reversibly, then we must have temperature which is just infinitesimally different than the temperature of the thermal reservoir. And by thermal reservoir we mean that the temperature of the thermal reservoir does not change. So only way the system can absorb heat from a high temperature reservoir reversibly or reject heat to a low temperature reservoir reversibly is through an isothermal process. And if this process is not isothermal, then the temperature difference between the thermal reservoir and the system would be finite. It will not be infinitesimally small, and therefore the heat transfer would not be reversible. So if you want to construct a system that operates in a cycle but reversibly takes in heat from a high temperature reservoir and rejects that heat reversibly to a low temperature reservoir, then the only way we can connect these states 1, 2, 3 and 4 are through these reversible adiabatic processes, because we do not want to have heat transfer in any other process other than these isothermal processes. So the only way we can achieve this is through having this Carnot cycle consisting of two isotherms and two adiabats. And that is why this Carnot cycle is depicted in this particular form, because this is the only way one can operate a heat engine reversibly by exchanging heat with two reservoirs at temperature θ1 and θ2. So how a Carnot engine can operate is that first you are at state 1, then in an isothermal process you can expand this gas, and let's say your piston rises up, so the volume has increased. Then you can lift some weight in a way we've shown over here in an adiabatic process by removing this grain of sand every time, so that we can slowly evolve the system from state 2 to state 3. Then you can again have heat transfer from the system to a low temperature reservoir, and that would bring down the piston, and thereafter you can add this, let's say, grains of sand to further take the system from state 4 to state 1. So therefore this is how in theory you can realize the Carnot cycle. But note that there's no way in reality you can have this quasi-static process. So what we are discussing is just a theoretical heat engine, but this is not the only way you can have a Carnot engine. In theory you can also have a power plant that is similar to the steam power plant that operates in a Carnot cycle. So there you will again have the high temperature and low temperature reservoirs, and let's call this as the high temperature reservoir and the low temperature reservoir. So in the boiler you, let's say, take in heat QH and you heat the working substance, which is fed to this turbine that produces net work, and the exhaust of the turbine, so whatever comes out of the turbine goes into the condenser that rejects heat, let's say QL, to the low temperature reservoir, and then we have a pump or a compressor that pumps the working substance back into this boiler. So therefore this whole system over here can theoretically operate on a Carnot cycle. And note that this compressor is also operated by the work that is partly done by the turbine. So the net effect is that you take in heat from a high temperature reservoir, dump it to the low temperature reservoir in two isothermal processes where temperature difference between the boiler and the high temperature reservoir is infinitesimally small, and the temperature difference between the condenser and the low temperature reservoir is infinitesimally small, and the processes within the compressor and the turbine are ideal and reversible, and there's net work output. So such a device can also, in theory, operate on a Carnot cycle. So we have seen that a heat engine that operates on a Carnot cycle takes in heat Q1 and rejects heat Q2, and in process does work Q1 minus Q2. So the efficiency, as we've seen for any heat engine, would again be given by Q1 minus Q2 over Q1. That is the work that this engine is producing over the energy that is supplied and that costs us, that is Q1. So you have efficiency is 1 minus Q2 over Q1, which is same as for the other heat engines. Now, note that a heat engine that operates on a Carnot cycle works reversibly. This means that the cycle can also be reversed because the cycle is reversible, so we can run this cycle in the opposite direction as well. Therefore, a Carnot engine can also operate as a refrigerator. So in that case, if you have this refrigerator that is opposite of this engine operating on a Carnot cycle, then it will consume work which is Q1 minus Q2, and this refrigerator will extract heat Q2 from a low temperature reservoir at temperature theta 2 and will reject heat Q1 to a high temperature reservoir at temperature theta 1, and Q1 is greater than Q2, and the work that is supplied in one cycle to operate such a refrigerator on a Carnot cycle is equal to Q1 minus Q2. Now, Carnot shows that the efficiency of a Carnot engine is independent of the working fluid, and this statement is extremely important because based on this statement we are going to arrive at the definition of the absolute thermodynamic scale of temperature. So to understand why efficiency of a Carnot engine is independent of the working fluid, let's consider two heat engines. So let's consider two heat engines, E and E prime, which are operating on different working fluids but between the same thermal reservoirs theta 1 and theta 2. So let's say you have this thermal reservoir at high temperature and you have another thermal reservoir at low temperature. Then we have this engine E that takes in heat Q1 and from high temperature reservoir and rejects heat Q2 to a low temperature reservoir and does some work. And we'll also consider another heat engine, let's say E prime, and this heat engine also produces the same amount of work, but it has a different working substance. So in general, we can first start by the assumption that it takes in different amounts of heat Q1 prime and rejects different amount of heat Q2 prime. So let us assume first that the efficiency of engine E prime is greater than the efficiency of engine E. So our aim is to show that efficiency of a Carnot engine is independent of the working fluid. So we assume first that this is not true and efficiency of one of the engine is greater than the efficiency of the other engine. So in our case, both of these engines deliver the same amount of work. So the absolute value of the work is W, so that we don't confuse with our sign convention. So efficiency eta prime is given by this, and this is greater than, so we've considered heat engines that deliver same amount of work but take in different amount of heat. So this equation implies that we should have this, but W, that is the work delivered by these engines, is the same. So we can also write this as Q1 is greater than Q1 prime. So in other words, if our engine E prime has higher efficiency, it means that to deliver same amount of work, it takes in less amount of heat Q1 prime. Now, what we do is that because Carnot cycle is reversible, we can have this engine E working in the reverse direction as a refrigerator. So what we can do is that we'll say that this engine E is working as a refrigerator, that is a Carnot cycle in reverse. So it takes this work that is output from engine E prime as the input and now absorbs heat Q2 from the low temperature reservoir and rejects heat Q1 to the high temperature reservoir at temperature θ1. Now, if you consider this combined system of both of these engines, that is engine E prime and this engine E that is operating as a refrigerator based on a Carnot cycle running in the opposite direction, then the net effect is that you have this high temperature reservoir θ1 and the low temperature reservoir θ2. So the combined effect of this system is that it operates in a cycle. Clearly, there's no work input to this combined system of engine E and E prime because the work delivered by E prime engine is being fed to this refrigerator E running in reverse, and there is some heat transfer between the system and the thermal reservoirs. So we know that Q1 is greater than Q1 prime, so the net heat transfer from this combined system is to this high temperature reservoir, which is Q1 minus Q1 prime, because Q1 is the heat that is being rejected to the reservoir and Q1 prime is the heat that is being absorbed from this high temperature reservoir. So the net effect is that the combined system or the combined engines, they are rejecting heat to this high temperature reservoir, and that heat is Q1 minus Q1 prime. Now if you look at this combined system over here, then it is operating in a cycle. So you can apply the first law of thermodynamics, and when you apply the first law of thermodynamics, the net heat that is being transferred to this combined system is this Q1 prime plus Q2, and there's no work that is being delivered or produced by this combined system, so that should be equal to the net heat that is being rejected from this system, and that is Q2 prime plus this thing Q1. So in other words, Q1 minus Q1 prime is equal to Q2 minus Q2 prime, and this is exactly the amount of heat that is being absorbed from the low temperature reservoir, that is Q2 minus Q2 prime, and that is equal to this amount of heat Q1 minus Q1 prime. So the combined effect of both of these engines is that you have a device that is operating in a cycle. It consumes no work, but it extracts this heat Q1 minus Q1 prime from a low temperature reservoir and dumps it to a high temperature reservoir. Therefore, this device violates the Clausius statement. And we have already seen that the Clausius statements and the Kelvin-Planck statements are equivalent. So this assumption that efficiency of the Carnot engine E prime is greater than the efficiency of another Carnot engine operating with a different working substance is a violation of these simple statements, that is the Clausius statement and the equivalent Kelvin-Planck statement. So our assumption that the efficiency of engine E prime is greater than the efficiency of engine E, and these engines are operating at different working substances, is a violation of the Clausius statement. Similarly, we can switch the roles of E and E prime, and we can say that if we assume that efficiency of engine E prime is less than the efficiency of engine E, then again it will be a violation of the Clausius statement. So both of these statements violate the Clausius statement. Therefore, we conclude that the efficiency of the Carnot engine is independent of the working fluid. So no matter what working fluid you choose, the efficiency of a Carnot engine operating between the same thermal reservoirs at temperature theta 1 and theta 2 are going to be the same. That means, recall, the definition of efficiency is 1 minus Q2 over Q1 is function of theta 1 and theta 2 only. In other words, we can also write that if you look at this 1 minus Q2 by Q1 is a function of theta 1 and theta 2 only. We can also say that Q1 over Q2 is a function of theta 1 and theta 2. So what we conclude is that all reversible heat engines which exchange heat only at temperatures theta 1 and theta 2 have equal efficiencies. And from this we concluded that Q1 over Q2 is a function of the temperatures of the thermal reservoirs, that is temperatures theta 1 and theta 2. Here this function f denotes a universal function which is independent of the working substance and the design of the heat engine. So in the next lecture, what we're going to do is that we're going to use this statement, which is expressed mathematically as this equation, to arrive at the absolute thermodynamic scale of temperature. And that would be the first step to prove the first part of the second law. So by proving, we mean that we want to arrive at the first part of the second law based on the Clausius statement, because this conclusion that we have derived is based on the Clausius statement. So if you recall that we've discussed in the previous lecture that the first part of the second law states that there is a property called entropy, which is derived by taking the ratio of the heat, and that is added divided by the absolute temperature, and summing all these terms over a path that is a reversible path. Then we've said that we are going to derive the definition of the absolute temperature during our so-called proof of that particular first statement. Therefore, what we are going to do in the next lecture is that using this equation, we are going to show that there must be a temperature scale which we'll call as an absolute thermodynamic scale of temperature, which must be independent of the properties of a thermometric substance, and that derivation requires use of this particular equation.